Hi everyone, I'm Dr. Senthilkumar Selvaraj, working as a assistant professor in Department of Electronics and Instrumentation Engineering. So today we are going to discuss about what is the kinematics in robotics. Today we are going to discuss minimum 3 topics like what is the kinematics and what is the forward kinematics and inverse kinematics in robotics, and how to write the kinematic equation for 2-axis robot arm. So first of all, what is the kinematics? So the robotics is the classical physics. Okay, so engineering is completely based on the physics and mathematics only. So in robotics is completely based on the classical physics. So you know very well what is statics, dynamics. You know what? First, what is the statics? Actually, I have one object here, and then I'm just applying one force. It is F1 I'm considering. I'm applying the same opposite equal force F2. That means F1 is equal to F2. So I'm applying equal force on both sides. Automatically the object can't move. It will stay in same position. So that is the statics. And dynamics, I have one object, I'm applying force here, automatically the object will move one position to another position, it will change the position. So here I'm considering in statics, I'm considering the force. Okay, but dynamics, I'm applying the force, automatically object will move one place to another place. So I have to consider the time, distance, displacement, acceleration, and everything. So force. So in dynamics, I'm applying force, automatically the object will move one position to another position. In that time, I have to consider this time, distance, displacement, acceleration, force, and velocity, and everything. Okay, so in dynamics, we have two types. So one is the kinetics, another one is kinematics. So kinetics is nothing. When the object is moving, I am just considering only the force. That is the kinetics. In kinematics, I am considering this all, like time, distance, displacement, acceleration, velocity, force, and everything. I'm considering the time of the object motion. So it is called the kinematics. So the kinematics also have two types. One is forward or direct kinematics, and second one is the inverse kinematics. So the dynamics have two types, that is the kinetics and kinematics. The kinematics have two types, that is the forward or direct kinematics or inverse kinematics. Okay, so now what is the forward kinematics? So forward kinematics means is nothing. Forward kinematics based on the joint angle and link length, I have to identify the end effector position. So this is called the forward kinematics. So based on the joint angle. So what is meant by joint angle? So I have one fixed robot, the base is fixed, and I have two joints, an end effector, and then I'm using some kind of two-jaw gripper. Okay, this is some different one type of the robotic model. Okay, so here I'm using two joints, joint 1 and joint 2. We are telling this is called some different type of the rotary joint. So previous video I just explained, discussed about the different type of the joints. So here I'm using rotary and then prismatic joint. So what is by rotary? Rotary means it will rotate. Okay, so it will rotate. And prismatic joint is the linear motion. It will move forward and backward and then left and right, up and down. So only the linear motion. So when we are using the rotary joint, in that time you have to identify the joint angle theta. So when I'm using the prismatic joint, it is a linear motion. So I have initial position, final position. So I have to identify the distance d. Okay, so based on the joints, you have to identify the distance of the distance, otherwise the joint angle. So here, this is the link length. So this is the link length. This is the link 2 and this is link 1. So like this is the one link, this is the another link. So this link length. So based on the link length and then the joint angle theta. So we have to identify the end effector position. So what is the inverse kinematics? Inverse kinematics is nothing. Now I know the end effector position. I know the end effector position. From the end effector position, I have to identify the joint angle. Joint angles. Okay, that is the theta. This is the inverse kinematics. Okay, so first, based on the joint angle and link length, I have to identify the end effector position, that is the forward or direct kinematics. Forward or direct kinematics. And with I have the end effector position, I know very well. So now from the end effector position, I am identifying the joint angles, that is called the inverse kinematics. Okay, that is the difference between the forward and inverse kinematics. So now how to identify the forward and inverse kinematics? Okay, so now how to identify? For example, in forward kinematics, now I know my joint angle and the link length. First, I have to identify the end effector position. How to identify the end effector position? So now, for example, I have two links in my robotic system. Link 1 and link 2. L1 and L2. Okay. So we have Y and X axis. Okay. This is my link 1 and this is the link 2. Clear? So this is the link 1 and this is the link 2. So here, listen, this is the end effector position I have to identify. Okay, so now I don't know my end effector position. Now I know my joint angle and link length. So now based on that, I have to identify. Why we are identifying end effector position? Because the gripper, it will attach with the end effector. So automatically, if you identify the end effector position, you can identify your material position also. Okay, so okay. So here, this is the link 1, this is x1, this is the y1. This is the x-axis for link 1, y-axis for link 1. This is the x-axis for link 2 and y-axis for link 2. Okay, so now I have to identify each and every link's x distance and y distance. Okay, so this is the x1 distance is the link 1 for link 1 and x2 distance for link 2. This is the y1 distance for link 1, y1 distance for link 2. So now x1 and x2. x1 plus x2. Okay. So the total x distance. What is the total x distance? This is the entire robotic model x distance I have to identify. So the total x distance is equal to x1 plus x2. So x1 is the link 1 x distance. x2 is the link 2 x distance. And the total y distance for entire robotic system, y is equal to y1 is the link 1 y distance and y2 is the link 2 y distance. So now I identified link 1 and link 2, x1, x2 and y1, y2. So x distance and y distance identify both links. Now based on this x1, x2, y1, y2, I identify the total robotic system x distance and y distance. So now how can I identify? See, now I know the x distance. The total x distance is here and total y distance is here. Okay, so y and x. So now the meeting point, it is called the end effector position. It's clear? So this is the total x distance including link 1 and link 2 also. This is the total y distance. This is the complete robotic system, link 1 and link 2, including link 1 and link 2. So now the total x distance and y distance identified means automatically the meeting point I can identify very easily for my end effector position. Okay, so this is the forward kinematics. Clear? So now I know the end effector position. Based on that, I have to identify the each theta 2 and theta 1. That is the inverse kinematics. Clear? Based on the end effector position, you have to identify the joint angle. That is the inverse kinematics. Clear? So now I will explain how to identify the kinematic equation for the 2D arm. So that is the forward kinematics. So forward kinematics for 2D arm. Clear? So now I just draw the diagram. This is the y-axis, x-axis, and then this is the link 1, link 2, and then this is the theta 1, this is the theta 2, this is theta 1 plus theta 2. Okay. So what is the L1? L1 is the length of the link 1. So this is the length of the first link. L2 is the length of the second link. And what is the theta 1 means? It is the angle of the first link with respect to the reference frame. So we are calling this is the reference. Okay. So theta 1 is the angle of the link 1 with respect to the reference frame. Okay. And theta 2 is the angle of the first link with respect to the first link, because the link 2 motion completely depends on the link 1. Okay, so the angle theta 2 angle, it is the angle of the link second link, sorry. So this is the angle of the second link and with respect to the first link. Okay, theta 1 plus theta 2 is the angle of the second link but with respect to the reference. Okay, so this theta 1 and theta 2, it is the angle of the link 2 but it is the reference respect to the reference frame. Okay, so this is called reference. So this is the theta 1 and theta 2. Okay, so now how to calculate the x distance and y distance, we just explain. So how to calculate the, I already told you how to identify the end effector position from the in forward kinematics. Okay, so in forward kinematics, how to calculate the x distance and y distance. So first we will check the x distance. Okay, so I told you for link 1, x1 and y1, that is the x distance and y distance for link 1, and link 2, x distance and y distance. So it is called the x1, y1 and x2 and y2. So then to calculate the total x and y distance. Okay, so first I am considering link 1. Okay, so here in link 1, I am just considering the triangle here. This is the theta 1 and this is the L1, Y1, X1. Okay, so here L1 is the length of the first link and Y1 is the y distance for link 1 and x distance for link 1. Okay, so now from here the cos theta 1 is equal to x1 by L1. So x1 is equal to L1 cos theta 1. So when you are considering the x-axis, you have to mention the terms in cos theta, and then when you are considering y-axis, you have to mention the angle is the sin theta. Okay, so now in y-axis, when I am considering sin theta 1 I told already, theta 1 is the angle of the link 1. Okay, so theta sin theta 1 is equal to y1 by L1. So the y1 is equal to, I am moving here, so L1 sin theta 1. So this is my link 1 x distance and y distance. Okay, so and link 2, I am considering a triangle. This is the L2, X2, Y2, but angle I'm considering the theta 1 plus theta 2. So I told you what is the theta 1 plus theta 2. Theta 1 plus theta 2 is the angle of the link 2, but with respect to the reference frame. Okay, so this is cos theta 1 plus theta 2 is equal to x2, that means and x distance and link length. Okay, so x2 is equal to L2 cos theta 1 plus theta 2 and sine theta 1 plus theta 2 is equal to y2 by L2. So automatically this is the y distance for link 2, this is the y distance for link 2, this is the link length for link 2. Okay, so distance, so now we are just identifying the x distance and y distance for the link 2. Okay, so y2 is equal to L2 sine theta 1 plus theta 2. Okay, so now I identified my link 1, this is the link 2 x distance and y distance. So now already I told you how to identify the end effector position, the total robotic system x distance. Okay, so x1 plus x2, link 1 x distance plus link 2 x distance. So total distance y is equal to link 1 y distance plus link 2 y distance. So we identified x1 plus x1 y1 x2 and y2 and everything. So now the total x distance is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. So y distance is equal to L2, sorry, here it is a sign. Okay, cos. So L2 L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Okay, so now y distance I'm mentioning in sine and x angle I'm just mentioning in cos. Okay, so the total x distance is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, and y distance, total robotic system y distance is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So this is the total x distance and y distance for the 2D arm. Okay, so now based on that, now I know the total x distance and y distance. Okay, so this is my x axis, y and x axis. So now I know the total x distance and y distance. Okay, so total x distance, y distance means this is my x distance, this is my y. So if you connect the lines, automatically the meeting point, it is for the end effector position. Okay, so now this is my end effector position. So now I considering the link length L1 and L2, and then joint angles theta 1, theta 2, theta 1 plus theta 2. Okay, joint angle. So joint angle and link length. Based on that, I identified end effector position. Okay, this is the forward kinematics. This is the forward kinematics equation for the 2D arm. Okay, so like that, how to write inverse kinematics? So forward kinematics, you know very well. So I told you forward kinematics means based on the joint and link length, identify the end effector position. The inverse kinematics is different. So from the end effector position, you have to identify the joint angles. That is the inverse kinematics. Okay. So now I draw the diagram first. So I'm just considering this 0. This is my x and y. And then you know very well, this is the theta 1. This is the link 1 angle. And after that, so this is the L1, this is the L2. I'm considering this is the B, this is the A, and O dash. Okay. So now this is the, I told you, this is the angle theta 2. Okay. And this is the pi. I'm considering there is a pi is equal to theta 1 plus theta 2. Okay. So now this is my total y distance, x distance, and then y distance. This is the y distance. That means base to end effector. Okay. This is the total y distance from the same end effector. This is the x distance, total x distance. Okay. So in forward kinematics, I already identified the total x distance L1 cos theta 1 plus L2 cos theta 1 plus theta 2. And then total y distance is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. So this is the total x distance and y distance for the robotic system. Okay. In forward kinematics, we already identified the end effector position. So this is the inverse kinematics. So I just considering the total x distance and y distance equations. Okay. So now how to calculate? So I told you inverse kinematics means from the end effector position, you have to calculate the joint angles. So how to calculate the joint angles theta 1 and theta 2? Okay. So here we are using the Pythagoras theorem. So Pythagoras theorem, you know very well, that is the a square plus b square is equal to c square. So you know the two side, you can identify the another side. So we are using the Pythagoras theorem. Now I am just OB square is equal to O dash square plus O dash B square. That means I am just considering this particular part. O dash B. Okay. So the complete angle O dash B. Okay. O dash B. It's clear. So now in the triangle, BAO dash. So what is the BAO dash? BAO dash. So this triangle. Okay. So BAO dash. Clear? So in this triangle, sin theta 2 is equal to O dash B by AB. So O dash B is equal to sin theta 2 into AB. So O dash B is equal to sin theta 2. What is the AB? See, the AB is the link length. So length of the link 2. Okay, so that is the L2. So AB it is a L2. So that's why I'm just replacing AB is L2. Okay, so this is the O dash B. Clear? So it's clear. AB is the length of the link 2. That is the L2. So that's why here in AB I just replaced L2. Okay, and then cos theta 2 is equal to O dash A by AB. Okay, that means the x-axis and the y-axis also now I am considering. So O dash A is equal to cos theta 2 into AB, and O dash A is equal to cos theta 2 again AB is the length of the link 2. Okay, so this is the length of the link 2. So I replaced L2. So this is my equations for O dash B and O dash A. Next, a triangle I am considering OBO dash. Okay, so that means OBO dash, OB and O dash. Okay, so OBO dash, O dash is equal to OA plus O dash A. Okay, that means listen here, O dash. So okay, O dash, it is the complete length of the robotic system. O dash. So what is the O dash? This is the OA plus O dash A. Okay, so if you add link 1 OA, and then O dash and A, so that's why I mentioned here O dash. So this is the O dash is the complete length. This is the link 1. This is I mentioned point A. Okay, in total link of the robotic system. So this is the OA, O dash A plus O dash A. So that means link 1 and link 2. Clear? So now O dash is equal to OA. What is by OA? So OA is the L1, link 1. So link 1 plus O dash A we already identified. So O dash A we already identified, that is the O dash A is the cos theta 2 into L2. Okay, so this is the O dash A. So O dash A, you substitute here, you will get L2 cos theta 2. Okay, then OB square is equal to O dash B square plus O dash square. Okay, so what is the OB square? So this expression. Okay, so this expression OB square is equal to O dash square plus O dash B square. Okay, so here now O dash B we already identified. So O dash B we already identified here. Okay, so that's expression substitute here. So O dash B is the L2 sine theta 2 whole square plus O dash is the we identified here O dash expression. So substitute here O dash square. So L1 plus L2 cos theta 2 whole square. Okay, and after that, what is the OB square? OB, it is the X plus Y term. Okay, so X square plus Y square. So the OB we are considering X distance and then Y distance also. So X plus Y, X square plus Y square is equal to L square, L2 square sine square theta 2 plus A plus B whole square form. Okay, so A square plus B square plus 2AB. Okay, so this form is the A plus B whole square form. Okay, and this is the 2L1 and L2. I'm moving this side. So 2L1 who is there? So here you just see L2 square and L2 square. L2 square sine square theta 2 plus L2 square cos square theta 2 is there. Okay, so I will take outside L2 square. So sine square theta 2 plus cos square theta 2 plus L1 square plus 2L1 L2 cos theta 2. Okay, so now sine square theta plus cos square theta, you know it is the 1. So L1 square plus L2 square plus 2L1 L2 cos theta 2 x square. Left hand side you have x square plus y square. Okay, so now I will keep sine, I will move this side. So this both I will move this term. So you will get x square plus y square minus L1 square minus L2 square is equal to 2L1 L2 cos theta 2. Okay, then I will move this to L1 and L2 to left hand side. So I will get the expression is cos theta 2 is equal to x square plus y square minus L1 square minus L2 square by 2 L1 L2. Okay, so now I need the angle theta 2. Okay, so theta 2 means I will move cos right hand side, so cos inverse x square plus y square minus L1 square minus L2 square by 2 L1 L2. So this is the final equation for to identify the theta 2. Okay, so now I already told you pi is equal to theta 1 and theta 2. If you know the total angle, entire robotic system angle, entire angle, theta 1 plus theta 2 is the pi. So now I know the total angle, and then now I identify the theta 2. So now it's very easy to identify the theta 1. So theta 1 is equal to pi minus theta 2. Okay, so this is the equations, kinematic equations for inverse kinematics equations. So this is the inverse kinematic equation for 2D robot arm. Okay, so again I'll just recall the previous one. So what is the forward kinematics? So for what forward kinematics means, based on the joint angle and link length, you have to identify the end effector position. That is the forward kinematics. Okay, and what is the inverse kinematics now? So now I know in forward kinematics I identify the end effector position. So from the end effector position I have to identify the joint's angle only. Here I am not considered the link length. Why? What's the reason? Link length means it never changes. So initially I just designed my robotic system. I just finalized this is the work envelope. Okay, so based on that I just selected my link length. I designed my robotic system. Angle will change, but link length it won't change. Okay, so that's why in inverse kinematics I am not considered the link length. I'm just identifying the joint angle. Okay, so if some motion is there, definitely the joint angle will change in robotic system. So automatically I have to identify the joint angle only, not link length. Okay, so this is the inverse kinematics. Okay, so in forward kinematics, the for total x distance and y distance you have to identify. From the x distance and y distance you have to identify the end effector position. Okay, and inverse kinematics, so in inverse kinematics, end effector position, and I have to identify the joint angle. So end effector position, x distance and y distance I know. From the x distance, y distance, I have to identify the angles theta 1 and theta 2 because this is the 2D arm. Okay, this is the 2D arm. I have only the link 1 and link 2, and then joint 1 and joint 2 only I have. So I used the two joints, and two joints also I am using the rotary joint. So that's why I am identifying the theta 1, theta 2. In case I am using the linear motion joint, that means a prismatic joint I am using, means I have to identify the distance, not angle. Okay, so here the both joints I am using considered the rotary joint. Okay, so that's why here I identified the joint angle theta 1 and theta 2 also. So this is the inverse kinematic equations for the 2D robot arm. Okay, so like that we are kinematic equation, we can write the kinematic forward kinematic equation, inverse kinematic equation for the Puma robot, and then a Scala robot. So different type of the robotic models, you can use the DH representations method. You can write the kinematic equation for the particular robotic motions. Okay, this is the basic 2D arm only. Okay, so like that we have the four axis, 6 axis, like that robotic system we have. So based on the robotic model links and joints, we have to write the kinematic equation. You have to identify the end effector position. Okay, so that is the forward and inverse kinematics. Okay, I think so this video is very useful to all. So we'll see in next video with one unique content. Okay, so thank you very much to all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.